Think of the color red. What comes to mind? Perhaps you know that there is a specific wavelength in the light spectrum that corresponds to red, and indeed there is. But what does this mean for you and I? Excuse the pun. What if I asked, do you see red the same way I do? In the eye, we have small cells that are sensitive to light. These cells are called rods and cones. The cones are sensitive to actual light colors. How this works is that light itself is a movement of photons which have a relative power. This is through the oscillation of these moving photons which are experienced on the sensitive photoreceptors. Red cones will be stimulated by more light in the red wavelength band, similarly for green and blue. Okay, so does this mean that all we need is a red wavelength of light to come into our eye for us to see red? Not quite. The cone spectral sensitivity graph explains where cones experience stimulus from light wavelengths. We can see that a particular cone is not exclusive to a specific wavelength, as we can see in this graph. A red cone does not only cover one spectral wavelength and switches on and off when that wavelength hits it. The red, green, and blue cones are sensitive to a range of wavelengths with varying sensitivity, and their spectral sensitivity overlap. We will see what that means in a moment. If we look at three light waves of red, green, and blue, we can see that they differ in wavelength. Any source of light comprises of a combination of these wavelengths imposed on top of one another. Therefore, we know that any source of light will have a portion of these three wavelengths with various relative power in it. This basically means that one wavelength could have a higher amplitude in the light source. Now, an important concept to understand is that every object and surface has a reflection factor. That means that when the light source hits the object, a portion of the light is absorbed by the object, meaning that the absorbed wavelengths do not bounce off of the object it is hitting. But there is a portion of light at a specific wavelength that does bounce off. This is the portion of light that makes it into our eyes. This is a portion of light that we see, or more accurately, it is the light stimulus, the light which stimulates our cone cells. When the red cone experiences the stimulus, it has no idea what it is seeing exactly. When the light that hits it is at its optimal stimulus wavelength, it requires a less intense light source for the cell to have a response. However, if a more intense light source of a different wavelength hits the same red cone, it will produce the exact same response for that specific cone. So if a green light with high intensity hits a red cone cell, it can produce the same red stimulus response as a red light with lower intensity. This is what's so interesting. There are infinitely many possible light spectra, but your eye reduces them to three cone signals, as we have seen. That compression creates metamerism. Two totally different spectra can produce the same cone responses, and therefore the same perceived color. So even if two people both say this is red, the physical light could differ and your visual system still lands on the same label. Now that we know the basic mechanics of what our eyes are doing, on top of that, people aren't identical senses. The exact filtering in the eye, like lens and macular pigment, and even details of cone photopigments vary across individuals. These are what help the photoreceptors produce the response from a light stimulus. There is also the case of color blindness. This is where a person might not have the apparatus to even see the color red. Red-green color vision deficiencies are much more common in men because they only have one X chromosome. Women carry different opsin variants on each X chromosome, leading to greater variability, and in rare cases, tetrachromacy. This is when a person can experience the world in more colors, up to 100 million colors, far more than the average person. This is due to having an extra cone cell in the eye. So, do we see red the same way? We share the same basic machinery, so we overlap a lot. But because perception depends on compressed signals, individual biology, and inference about the world, there's no guarantee that the qualia of red is identical. What's remarkable is that we still coordinate well enough to build traffic systems, arts and science, on top of that messy but brilliant biology.